When you're counting permutations that contain identical items, you have to be really careful because when you count them the usual way, what you will have actually done in this case is you'll have counted identical things more than once. So you need to make up for that. So my tip is calculate your permutations the usual way and then stop and consider how many of your permutations will actually be identical and divide your answer by that number or those numbers. So easiest way to see how to do it is to look at an example. How many 7-letter words, and by words we just mean combinations of letters, can be made by rearranging the letters in the word dresses? So first just check that there are actually 7 letters in dresses. There are, so we're going to need to use all of them. Now we can see that some of the letters are the same. There's actually 2 E's in this word and there's 3 S's. So our usual way of calculating the number of different permutations would be to say, well, there's 7 different letters we can put in the first position, and then 6 in the next, and 5, and so on. So our usual method would give us 7 factorial. But now we need to divide our answer by the number of identical words. Now, let's just consider the E's for a minute. If we swapped these 2 E's around, it'd still say dresses, and nobody's going to think that they're 2 separate words. They're literally going to look exactly the same. So every single one of these 7 factorial words that we've come up with is going to have the possibility to make it 2 ways depending on how you place your E's, and both of them are going to look the same. So we've overcounted by a factor of 2. So we need to divide by 2 to make up for that. Now looking at the S's, if there's 3 of them, how many ways can you arrange those 3 S's, even just in the word dresses here, so that they're going to actually spell out the word dresses? Well, there's 3 of them. So you can place your 3 S's in those 3 positions in 3 factorial ways, because there's 3 S's you can put in the first position, 2 in the next, and 1 in the last. So for every single one of our 7 factorial words that we've come up with, we could rearrange the S's 3 factorial ways and get the exact same word. So we must have overcounted by 3 factorial just for the S's. So this is what we need to do to come up with our answer. Now using your calculator and just being careful that the factorial is actually on the bit that it should be on. Whoops, 7 over 2 times 3 factorial, and we get 420. Now something interesting happens when there's only 2 types of identical items to choose from. And the easiest way to understand it is to have a look at an example. And in fact, this sort of work is going to be important for understanding our next section of work on combinations that are not ordered. So how many ways can I line up 5 identical wine glasses and 3 identical tumblers on the shelf? Well, how many glasses are there altogether? 8. So if I was just considering them all as being different and not identical, I'd say that there's 8 factorial ways that I can line up each individual glass. But if I can't tell one wine glass from another, and I can't tell one tumbler from another, then there's a lot of these arrangements that actually look exactly the same, and for all intents and purposes are the same. So we need to divide by those. Now, how many ways are there of arranging the 5 wine glasses into 5 positions? Well, for any of these permutations that I've come up with, no matter where I've put the wine glasses, there are a bunch that look the same, and there's 5 factorial of them that will look the same, because I can arrange 5 things into 5 positions in 5 factorial ways. And similarly, there's 3 factorial ways that I can arrange the tumblers. Now, the interesting thing you'll note is if there's only 2 things to choose from, then these 2 numbers here will add up to the number on the top. And so we get a situation where if we've got n things, and we could say that r of them are of one certain type and the rest are all another type, and there's only 2 types, then what we're going to end up with is r and n minus r, because you'll notice that with only 2 types, however many you have of one thing, you have that minus that of the other thing. And this is something that you'll see in later units, and you'll think, that's quite related to that work we're doing with our permutations. Now, the answer to this question here is 56 different ways. But a quick thing to note here is that even though it's fine to write 5 factorial, 3 factorial without any multiplication sign, because we can leave that out and just assume that it's there, when you go to put it in your calculator, you still need to put that times sign. There's some multiplication signs that you can leave out on your calculator, but this isn't one of them. Some questions involving counting permutations that have identical items in them will just be too complicated to do unless you use cases. So cases are great when the situation just seems too hard and you're trying to do it with a conventional method and you can see that there's great complexity. Try to minimize the number of cases just so there's less things for you to add together. Now, this example is a great one to illustrate how to do this. How many 6-letter words can be formed from the letters in dresses? Now, a minute ago we looked at the 7-letter words that we could make, and there are in fact 7 letters in dresses. The problem that comes about here, if there's only a 6-letter word that we're making, is which letter has been left out? Because if we just try and think about the 6 factorial ways that we could arrange the letters, we're not sure what to divide by because it's going to be different depending on whether we end up with 2 E's in it or 3 S's or maybe only 2 S's. And so there's too many unknowns. So the best thing to do is to consider what might be left out. It could be a D, it could be an R, it could be an E, or it could be an S. Add those together. Now, let's leave out an E first. So we'll consider what happens without an E. Well, how many letters will be left? 6, and we can arrange them 6 factorial ways. Now, without one of those E's, there'll only be 1 E that we're left with, but there'll be 3 S's, and they can be arranged 3 factorial ways. So we'll have to divide 6 factorial by 3 factorial, and that will give us 120 different ways. All right, what about if we leave out an S? That will leave 2 S's and 2 E's and a D and an R. Well, we could arrange those letters 6 factorial ways, but we'll need to divide by 2 factorial for the 2 E's and 2 factorial for the 2 S's. Now remember, when you put this in your calculator, to actually put the times sign in there between your factorials. Another quick hint, 2 factorial is just 2, so I'll generally just go, well, that's 2 times 2, I've just got 4 on the bottom, and just put that straight in. We get 180 different permutations there. Now we could consider leaving out the D and leaving out the R separately. I can see that they're going to be the same, so I'm thinking we should just do the D and the R, imagine what each one of them would be, and just double it. You can do them separately if you like, or just take this little shortcut. So let's consider if we take out the D or the R, let's start by saying we'll need to double whatever it is, and now we can just consider one of them. So leaving out the D or the R is going to leave us with 6 letters, and they can be arranged 6 factorial ways. But importantly, we're still going to have 2 E's and we're going to have 3 S's in it. So we're going to need to divide by 2 factorial, or just 2, and 3 factorial. So we've got, oh no, we haven't done that one yet. We need to do it again. 6 factorial over 2 times 3 factorial, and then we need to double that whole thing. So we'll end up with 120. So now, adding all of these together, our different cases, we've got 420 different words, 6-letter words that can be made from those letters.